This is a discussion of the extraction of caffeine from tea leaves. It's a typical undergraduate experiment. Caffeine is a white crystalline compound that is a psychoactive drug that's found in many plant materials, including tea and coffee. In this experiment, we're going to extract the caffeine that's present in between 6 and 8 tea bags, roughly the average amount of tea a person would consume in 2 days. Tea is a plant material that's been dried out, so the caffeine would have been present within one of the structures inside the plant cells. The method here is an extraction process to remove the caffeine from tea. In doing so, we need to remove the tea bag itself, the waste solid tea particles, remove the colouring and flavouring molecules that come out in the extraction with water, and to remove the tannic acid that's also present when you extract caffeine in the method that we have here. The extraction process is straightforward. The first thing we need to do is to rupture the cell walls of the tea and to hydrate its contents. This is what happens when you boil up tea bags. So we're going to boil the tea bags here for about 20 minutes on a hot plate. And we've also taken the opportunity to add some calcium carbonate to the mixture. One of the waste products that we don't want is tannic acid. Tannic acid will react with calcium carbonate to form a salt plus water plus carbon dioxide, and the calcium tannate formed is insoluble. After the boiling process, we will filter using Buckner Filtration. We will then cool down our filtrate, use dichloromethane as a solvent to do a solvent extraction. The caffeine is more soluble in dichloromethane than it is in water, and the dichloromethane will not react or dissolve in water. Once we have the caffeine in the dichloromethane, we will need to chemically dry it to remove any traces of water. Once that is done, we'll remove the drying agent with a simple filtration, gravity filtration, using a fluted filter paper, and then put the solution through a rotary evaporator to boil off at reduced pressure the solvent, leaving behind the solid caffeine. Once we have the solid caffeine, we can run a few tests. We can run some infrared spectrometry, and we can do a sublimation point using a boiling point apparatus. A brief word on safety. The chemist involved in the experiment is required to wear safety glasses, a lab coat and disposable nitrile gloves, and carry out the entire experiment in a fume cupboard because dichloromethane fumes are hazardous. Caffeine extraction experiment using a hot plate. Hot plates rather than Bunsen burners are employed in most laboratories because a Bunsen burner has a naked flame, and a lot of teaching laboratories and research laboratories use solvents that are inflammable. Even in a fume cupboard, you could be working alongside somebody else doing an experiment using an inflammable solvent such as cyclohexane. Having a flame around is not safe. Hot plates are effectively electric cookers. They have a thermostat that can be controlled either by a manual knob or by linking to a computer, which can program changes in temperature. Here we're simply putting tea bags, some calcium carbonate into a beaker, adding some hot water so we're not starting from a cold solution just to save time, and then using the hot plate to heat up the mixture for 20 to 30 minutes. This hot plate has also got a stirring mantle capacity, which is the knob on the right hand side. We're not employing that here. So we can stir and heat at the same time. It's a heater stirrer. Just a quick word about using kettles in laboratories. They have to be dedicated for experimental use only, and not the ones that you use to make tea on your tea break. At this early stage in our extraction, we have now got the caffeine in aqueous solution. We've also got the colouring molecules and the flavouring molecules dissolved. The calcium tannate has been formed from the tannic acid using the calcium carbonate that we added at the beginning, and we've still got the debris from the tea bags and the ruptured tea leaves. The next step is to remove the insoluble materials, leaving behind a solution, and we'll cool it down at the same time. In this next step of the extraction of caffeine from tea leaves, we're concentrating on the technique of Buckner filtration This is also called reduced pressure filtration. Gravity filtration, where you simply fold a piece of filter paper into quadrants, place in a funnel and pour your solution containing insolubilities through, is a slow process. In order to speed up the process, we employ a vacuum. The apparatus is set up using a thick-walled side-arm conical flask called a Buckner funnel, and that is clamped to make sure it's stable and connected to a vacuum line. Now, some vacuum lines can be powered by a water pump, others can be using a mechanical pump as we have here. There is a trap placed between the receiving side-arm conical flask and the pump, just in case of any overspill, to save any liquid entering the very expensive pumps. The Buckner funnel itself is ceramic, and on the base of the Buckner funnel are a lot of small holes over which sits the piece of perfectly cut filter paper. These are manufactured elsewhere. The filter paper is placed in the Buckner funnel. Itself is put into the Buckner flask via a rubber gasket. This allows a close fit. And in this particular apparatus, the Buckner funnel itself is sitting in an ice bath because we're filtering hot solution and we want cold solution for the next step in the process. As we're using water as a solvent here, water is used to wet the filter paper to ensure a good seal between the filter paper and the Buckner funnel before pouring in any of our mixture that's to be separated. That way, no solution can get under the filter paper at the very beginning of the experiment. Solution is passed through the Buckner funnel until the Buckner funnel shows evidence that it is no longer filtering. At that point, the vacuum line is turned off. Air is let back into the apparatus so that we can easily remove the Buckner funnel, change the filter paper, reset, and carry on. The way the Buckner funnel works is that by removing air from inside the flask below the filter paper, there's a lower pressure below the filter paper than above. Above is still room pressure, and that change in pressure helps push the solution through the filter paper. The filter paper, of course, will become blocked because the little holes formed from the fibers of the paper within the filter paper will become blocked with insoluble waste. In this particular case, the insoluble waste will be any broken tea bag loose leaves, but certainly unreacted calcium carbonate and calcium tannate that would have been formed when calcium carbonate removes the tannic acid from the original tea solution. All that we should be getting through the Buckner funnel at the end is cooled tea solution, which contains caffeine, colouring molecules, and also some flavouring molecules. There should be no insoluble impurities going into the next step. In this step of the caffeine extraction, we're going to employ the technique of solvent extraction. Solvent extraction is used where a material that we're after, whether it's a liquid or a solid, that's already dissolved in one solvent, is more soluble in a second solvent. Furthermore, both solvents in discussion are immiscible with each other. They don't dissolve in each other. In a caffeine extraction, caffeine dissolves in water but is more soluble in dichloromethane, DCM. Dichloromethane does not dissolve water, nor does it dissolve the impurities such as the colouring molecules and the flavouring molecules that are also found in the aqueous solution. To employ solvent extraction, a separating funnel is used. The solution that we're interested in is added to the separating funnel, and a fixed volume, a known volume of solvent, here dichloromethane, is added. The separating funnel has a stopper placed on it and is held firmly in place into the separating funnel and turned upside down and swirled. The vapour that's produced by the volatile solvent has to be released periodically, and since dichloromethane is not particularly good for the body, this has to be done within a fume cupboard. The separating funnel's tap is open to let through the lower layer. Whether the lower layer is the one that you're interested in or the upper layer is will depend on the density of the solvent. In this particular case, dichloromethane is the denser of the two solvent, and that is the one that contains the caffeine. The tap is used to limit the amount of aqueous solution coming through. Now it is far more efficient to use 3 solvent washes than it is 1 large wash of solvent. That can be proven mathematically. So the process is repeated at least once more. The dichloromethane solution is then collected, and the next step will be to dry it. The aqueous waste can be put down the sink at this point, and we should have removed the colouring and flavouring molecules, as well as the water. So just a quick recap. The dichloromethane now contains the caffeine, plus it may contain traces of water. We've got rid of all the insoluble materials and those which are more soluble in water, and left those in the aqueous phase. The next section should show you how to flute a filter paper. So why do we use a fluted filter paper? Well, the filtering is done because we need to remove the partly hydrated drying agents and any unhydrated drying agent. Now sometimes we can simply decant, pouring the solution off the top of the solid, but it's best to filter if possible. And a fluted filter paper is far more efficient than a filter paper just folded into quadrants as in the traditional school gravitational filtration. Caffeine extraction experiment: how to fold a fluted filter paper. Fluted filter paper has a larger surface area through which a solution can pass than a traditionally folded quadrant filter paper. This makes the filtering process more efficient. To flute a filter paper, fold the paper in half, then in half again, and in half again in the same direction. We should have 1/8 of a cone. This becomes origami for chemists. Unfold the cone twice so it looks like a semicircle. Now try a fan fold, alternative folding up and down every 8th section of the semicircle. Open the fan until you get a fluted filter cone. It's easier to do than it is to explain how to do. It's easier to see the video than to listen to the description. Next step, dry the solution using a chemical drying agent. In this section we're looking at the use of chemical drying agents. Even though the caffeine in dichloromethane has been separated from the aqueous layer, there will still be traces of water present, either as the odd drop in the dichloromethane that came about through inaccurate separation, or on the molecular level where water molecules will be within the mixture. We make use of drying agents such as magnesium or calcium sulfate or chloride, all of which have to be in the anhydrous state, so without water crystallization. There are other drying agents available such as conch sulfuric acid, conch phosphoric acid, etc. But you have to choose a drying agent that's not going to react with any of the solvents or the solutes. And of course you need to consider cost. The anhydrous salt of magnesium sulfate is used here, so we introduce that into our mixture, plenty of it, swirl around so that the anhydrous salt can hydrate, picking out any of the water molecules. Magnesium sulfate fully hydrated is 7H2O. Swirling allows the hydration of the salt to be more efficient. Filter off the drying agent using a fluted filter paper. Put the used drying agent to a suitable waste container. At this point we should have a solution of dichloromethane that is dry, into which we have the caffeine dissolved. Next step, remove the dichloromethane. The use of a rotary evaporator is a common skill in an organic chemistry laboratory. Rotary evaporation is used where solvents have such a high boiling point that heating them up may cause their solute dissolved in them to decompose. Some solvents are also inflammable, so using a Bunsen flame is not a good idea. That's why we use a water bath. What we need to do is lower the boiling point of the solvent, and we can do this by lowering the pressure under which the solvent is heated. So we use a closed system, sucking out gas molecules from the apparatus, that's the air and some of the solvent vapor. We can reduce the boiling point of the solvent considerably. It's then easier to distill out the solvent and leave the solute in this case behind. The apparatus is made up of a few distinct parts. Firstly, there's a vacuum pump to be able to remove vapour from inside the apparatus. Secondly, there's a water bath. Thirdly, there is a Liebig condenser, and here we have one fitted with 2 spirals of chilled water from a chilled water supply. And lastly, you have receivers for your product, and of course we have the round bottom flask containing our sample with its solute to attach it to the apparatus. This is the part that is sent to rotate and then gets lowered into the water bath. The rotation is to ensure that there is an even spread of solution in contact with all the surface area of the flask at any one time. This makes the process more efficient. In terms of efficiency, having a double spiral condenser allows more cooling surface area, again making the process more efficient. We use reduced pressure distillation to either get a solid from a liquid or a liquid from a liquid. And whether the product that you want stays in the original flask or in the receptacle flask depends on the experiment that you're doing. The way this works is that at reduced pressure, boiling points are lowered. In the experiment we're performing here, which is the removal of caffeine from its solvent, the solvent being dichloromethane, the pressure is reduced until the dichloromethane boils at the temperature of the water bath. The water bath here is set to less than 100 degrees centigrade. As the vapour comes off, it condenses on the cooler part of the apparatus. Eventually the solute will remain behind in the starting vessel, and the solvent will have condensed on the condenser and dripped down into the receptacle flask. To get the sample out, we need to stop the rotation, having raised the sample out of the water bath, bleed some air back into the apparatus so that the pressure is the same inside and outside the flask. Of course, we have to turn the pump off for that to happen, and then we can easily release the flasks that we're interested in. If all the steps have been carried out carefully, we should now have a dry sample of caffeine that can be analysed further. Normally we'd weigh the product inside the flask and then clean the flask out and then weigh the dry, clean flask afterwards to work out the mass of caffeine. The caffeine sample here could still have traces of the breakdown products of chlorophyll in it, but they would be in extremely small quantities. The 2 tests that follow, one will be running an infrared spectrogram of the sample and the other measuring its sublimation point. One of the standard laboratory tests is to take a melting point using a melting point apparatus. Now, unusually caffeine sublimes, but we will still use a melting point apparatus. Some sample has to be introduced into a very thin capillary tube that's sealed at one end. You cannot get any solid into a capillary tube if it's wet. Besides, the impurity, water, would alter the melting point or sublimation point. You need to tap down about 5 millimeters of solid into the sample tube. The sample tube is then placed into the electric heating element within the top of the melting point apparatus. Melting point apparatus come in many different shapes and sizes. All of them will have a heating block. They will also have a magnifying glass window to observe the sample in the heating block. The equipment that we're using here allows us to heat up very quickly to within 20 to 10 degrees below the sublimation temperature, and then increase the rate of heating slowly to get a good idea of the temperature range over which the caffeine sublimes. You just simply observe the changes taking place in the sample tube and then note the temperature range over which this occurs. All waste glassware then needs to be put into a glass bin for safe disposal. We can use infrared spectroscopy to look at the identity of our caffeine to check it is caffeine, and furthermore to check that it is dry. To do this, we need to clean off the diamond crystal that the sample will be placed on to make sure that no one else's residue has been left behind. We can use a simple solvent and a wipe for this. If this is the first time it's being used, we can run a background check just to make sure that the machine realizes we're performing these analyses in laboratory air. The spectrum of laboratory air will be removed from the sample spectrum. The sample is placed on the crystal. It doesn't require much, just a few milligrams. The reflective surface is screwed down onto the crystals and the software program is run. The software program here is chosen to run the spectrum 4 times and to take an average and remove any anomalies. The spectra that appears on the screen can be printed off or stored. We can look to see if a sample is dry. Usually you can tell whether the crystal material is dry because it sticks together if it's damp. But there should be some water around 3,500 wave numbers or greater, the left-hand side of the spectrum, if there's any water present. The OH in water is in a different place from the OH in both phenols and alcohols. If the crystals are damp, there'd be a large bulge on the left-hand side. Water has OH in hydrogen bonded form. This accounts for the broadening of the peak. We could just run the sample spectrum that we've obtained against the database and check that all the fingerprint regions are in the right position. Or we could just sample some of the key peaks. Once we finish with the IR spectrometer, we need to clean up the instrument ready for the next chemist that wants to use it. It's good lab practice not to leave any traces of unidentified compounds behind. Thank you for listening. If you've enjoyed this experiment, look out for the one on the synthesis of the solid anesthetic benzocaine.